All right. Welcome all. Thanks for being here. Today I'm going to talk about Polar's GPU engines, and also in particular the GPU engine. My name is Ritchie Vink. I'm the author of Polar's. I'm also the CEO and co-founder of the company Polar's. And I have originally a background in machine learning and software development, and if you go way back, civil engineering, but that's not really useful here. So today I'm going to talk a bit, I'm going to do a short introduction about Polar's for the people who don't know what it is yet. I'm going to talk about GPU acceleration, or in particular our GPU engine, and I'm going to talk about the different Polar's engines. So Polar's is a query engine for data frames. That's how I like to put it. And that's different to how people regard data frames traditionally more on single node machines. So traditionally in our data table or our data frame or pandas, the data frame was regarded as a 2D data structure within series, and you got data in it, and you can do an operation on this, and that operation will take the data structure and transform it into a new data structure, or transform that same data structure. But it's very much tied to a data structure. Like if you have a hash map, you can do an insert and extract. But I like to think about data frames a little bit different. We like to think more about the operations you apply to them. And we call those lazy frames, and those are more a DAG of operations. So every operation, we don't materialize your data frame immediately, we just create a new DAG, a new set of operations. We modify this set, but we don't do anything until you ask for this specific materialization. When you ask for materialization, so you say, give me the result, then we run a query optimizer. Once the query optimizer is done, we send it to the engine. The engine will load the data from the source, do the operations, and then we will get a data frame, an in-memory data structure. And then rinse and repeat. You can then use this data frame again to start a set of operations. But we like to think way more on the DAG, on the optimization, or on the total structure, but just not only on the data frame and the operations you can apply on those. So, in short, we're a query engine with a data frame frontend, and I always like to say we respect decades of database research. In the database field, there's tons of research in how we do query optimization, how we do materialization. There's tons of experience in optimization of data processing, and we should not ignore that. And there are tons of things we do. We minimize materialization, we use copy on write, we use sliceware operations. We have data types that are constructed to amortize access and allocation cost. It's written in Rust. That means we have full control over performance, over memory, over threading, over all the things that matter if you want to do very fast data processing. It's designed for effective parallelism. We have tight integration with I/O. Actually, the I/O we care about, we implemented from scratch. We have our own RK readers, we have our own CSV readers, we have our own arrow readers, and we ship with zero retry dependencies. So it's all in our binary. It's all in our in our binary. So as a result, we are one of the fastest open source query engines, together with tools like DuckDB or ClickHouse. We do really good on single node data processing. Here are 7 queries of we call this the PDSH. It's a derivative of the TPCH benchmark. The TPCH benchmark is a benchmark made for databases, and it's got all tons of questions that really test different operations. You can find more of this on our website. I don't want to tread on this too much. Today I want to talk about GPU acceleration. So this is something we just landed, I believe 1 or 2 months ago, I think 2 months ago, in cooperation with NVIDIA, and it's a GPU engine. And the design considerations for this were that it has the same semantics. This is super important. If you run a query on the CPU engine or the GPU engine, the results should be the same, right? The semantics should be the same. We also find it really important that we use the Polars optimizer. It shouldn't be the case that if you use a GPU engine that suddenly we read columns we didn't read before, that the join orders change, and it should have hybrid execution. That means if it cannot run on the GPU, it should fall back to the CPU and not raise an error. And it should be part of the Polars library. So we want to work seamless, and it should not be the case that you import cuDF Polars SPL as a different library, and that is a shim to the Polars API, because that's really hard to maintain. It might get out of sync, and it might do different things a bit differently than we do. So from a user perspective, nothing changes. You can write a query. Here on the top, we define a query, and then you can collect that query on the CPU by just writing collect. Or if you want to run this on the GPU, you can collect and you define the engine on the GPU, and you will get the same results. So I want to explain a little bit how we did this. And to do so, we have to look at the roadmap of a query. So in a query, the first thing you do is you write your query in Python, which is sort of the logical phase. If you write this query, you build a tree or a deck of operations. So you scan the bouquet, you apply the filter, you do a select, you take the limit, and we keep this tree of operations as a DSL, and then we convert it to an IR. And to explain a little bit better what that means, I'm going to take a little look in the notebook to give you some sense of give you an idea of what this means. So here on the top, is this visible, or should I zoom in? How do I do that? Well, that works. So here we create an expression. You can select a column with a regular expression. So here we take this regular expression, so anything that starts with FO and some rest, we multiply that times 2, and then you see we get this expression, and this is in DSL space. So that means this expression says take column fo and multiply it with some dynamic integer 2. And if we create a data frame and we apply this expression, so we select E, then we apply it, and we print this, we explain this, we can see that this dynamic integer materialized. So if you look here, column foo, the regular expression materialized in column foo times the integer 2, and here in column foo question mark times the float 2.0. So this is different from the DSL. So the DSL describes the operation, but it isn't defined yet. And on the IR phase, we took the schema of the input sources and we actually resolved what actual operations would be executed. We looked at the data types, the amount of expressions that are expanded, and we also will apply optimization. So if you look in this query plan, you see we still select, but that we only project 2 of 3 columns. So we only select 2 out of 3 columns, so the optimizer will ignore the 3rd column. So if you load a CSV file or you load a bouquet file, that means you won't read that column. Another thing is if I add another column, so I add fo, and then apply the select, we will get an error. And this error meant that the expression could not be resolved because we cannot, this is a string column, and we cannot multiply a string times 2, right? So this error occurred during the resolving of the IR and not during execution. This is an important distinction. So if you write a query, you will get these errors up front. And even if this is very deep down in a query plan, you will not get this error after 20 minutes compute, like you might have with something that works eagerly, because it doesn't know yet what times it will be resolved. So that's what the IR. So you go from DSL to IR, and then you go to an optimizer and to a physical plan. And the IR needs a schema. And to be able to have a schema, it needs to go to a sort of physical layer to get the schema. So you can, for instance, load data from S3. Then we need to download the schema from S3 before we can resolve the schema. Makes sense, right? So at this point, you go into an async data loader, fetch the schemas, already start the downloads up front, so we can keep downloading while we do the optimizations. When the optimizer is done, we get a physical plan, and we go to the engine. Is this sort of clear? Okay. Back to the slideshow. So, yeah, so this is all logical. There's no physical here yet, because, and by logical I mean we do some work, but we're not executing a query. We do work to determine what we need to do, how the expressions need to be expanded, what the schemas will be, what the data types will be, apply optimization so you don't do unnecessary work. And this is also the point where the cuDF callback falls in. So we go from logical, we go into a DSL, we convert to the IR, there we have the metadata, we have the schemas, we have the result names. Then we go into the optimizer, that's still on the CPU. Then we have an optimized IR, and that's what we send to cuDF as a callback. Then cuDF will traverse this IR and we'll see, okay, here you do a join operation, here you do a group by, we can replace this group by, we can replace this join with something we can execute on the GPU. So cuDF will give us a partially accelerated IR in return. And they can just insert a Python callback, which to Polars is just a Python callback with a promise that it returns a data frame of this schema. And when we go to the physical phase, we have an engine, we have our Polars in-memory engine, which starts on the CPU, does some operation. At one point it hits that physical GPU callback, and it calls into cuDF. cuDF does its work, materializes a data frame and gives it back to Polars. And you have sort of a hybrid between CPU and GPU. And this can work because our Polars in-memory engine, our default engine, is full batch, right? So you get a full data frame per operation. If you do a join, you get a full data frame. If you do a group by, you get a full data frame. And as a result, you get GPU acceleration. So here are some performance benchmarks on this executed by NVIDIA with a very high-end CPU and a very high-end GPU on the PDSH, a derivative of TPCH. And you see you get speed-ups from almost no, from 1.0 to up to 13 times. And the difference is mostly determined by how I/O bound you are. So if you're really compute bound, you get a lot from a GPU. So the query 18 and query 21 are very compute bound. There are a lot of joins. There's a lot of number crunching. There the GPU is great. If you have query 2, there's a lot of I/O work. There the GPU is twiddling thumbs and waiting for the data to come in. But no harm, no foul. It doesn't slow down either. So yeah, it's I/O bound. So what made this easy, quote unquote? One, NVIDIA's cuDF being available. Implementing this in Rust would have been a whole sub-project that we would not have engaged in. It was too much work. NVIDIA helped a lot. We worked together. It also made it easy because we decoupled the semantics from execution and logical, and we have a high-level IR which fits batch operations in cuDF. And so it showed that that's really powerful, that you can have one engine, and if you need a faster compute engine, you can use a GPU. And actually, Polars wants to give you engines for different tasks. If we look at the long-term trends in databases, this graph I borrowed this from Andrew Lamb from Data Fusion. You see that there are tons of databases over time. And there are a lot of databases because every database focuses on something different, and you have trade-offs. If you're really good in OLAP, you cannot be really good in transactional. You need immutable data to be very good in OLAP. If you're really good in time series, you have different trade-offs which make you a bit less good in other parts. If you cannot compile everything. Writing a query engine, you're always figuring out, okay, what do we compile from, which combination do we compile, and which operations do we dynamic? And it's a trade-off, and because of this trade-off, you see a lot of different database engines. And what these engines have in common is that they all have a SQL front-end, and it's pretty easy to switch between a database if you know SQL and find a database that's tailored to your needs. For DataFrames, this isn't the case per se. So for Polars, we've been focusing really a lot on in-memory data processing. It's something I think we're really good at. And we want to expand this because we're really good at linear scaling, and linear scaling brings you really far, but not everywhere. So we want to give you an engine for different data cases and different data scales. So if you're in memory, on tiny data till everything up to RAM, the in-memory engine gets you there. If you have a little bit more data and you're compute bound, the GPU engine can help you. If you have a little bit more data and it's still the data fits on a single machine, we're building a streaming engine that should be able to process any data set that fits on your disk instead of on RAM. And we're building a distributed engine, which will take you for the rest, for the data that doesn't fit on a single machine. So I want to take a little bit of explanation on how these different engines work, so you can get a sort of mental model. Our default engine is the in-memory engine. It's really focused on being fast on data that fits in RAM, but it should also be really fast on tiny data. So we want to compete with pandas on from 100 rows to 100 gigabytes of data, or 500 gigabytes, right? If your RAM allows it. So there are trade-offs here, and we really want to also include the very tiny data scale. This engine operates in batch, full batch. So you have a query here where you have an operation, you have a source, you have a join, another operation, other source, and on every data boundary. So if we read here, we read the whole data, and then we go into the next operation. So it's full batch. This there are some benefits here. It's simple. It's simple to reason about. Order maintaining is cheap. So if you do rolling window functions in general, time series is really fast because there's no overhead of communicating morsels of data order. We apply work stealing for parallelism. So work stealing means that you put work on a thread queue, and if there is a core finished and there is still work on another core, it can steal from that core and do that work. It's quite simple, but there's no control, but it gets us really far. It's fully parallelized, but we have parallel aware algorithms. So in a group by, we know how to parallelize. In a join, we know how to parallelize. But there's no parallelism inherited in the engine. It's in the operations itself. That makes sense. So that's the in-memory engine. We are building a streaming engine, and we're pretty far. It's now included in the binary in the next release, but it's not documented yet. It will be, I think the initial release will be in 2 months or so. There is already a streaming engine in Polars, but that was sort of a beta. And we learned a lot from that, and from what we learned, we built a new streaming engine. That's where I'm talking about now. What the streaming engine does, it processes data in chunks. So if you look at this, you can imagine a chunk flowing here and going into a pipeline, and then you have a, sort of the source loads the data, it gets into a filter, into a select, into your linearizer, and then in sync you write it away. And here we imagine 2 threads, and then the other the other data chunk can go here, and it will flow. For this, we made a custom async executor, a POLIS async runtime. We've written it from scratch. Is anybody here familiar here with Rust and async? Right. Yeah, so you have Tokyo, for instance, which is also a runtime. We made our own runtime because we want to be able to do task prioritization. So our scheduler can determine where the task needs to go, in which pipeline, and you can think of this as plumbing, and you put water in those pipelines. And if data is skewed and this pipeline gets way more data and is working longer on this chunk, but this pipeline is already ready, the data will just flow into the streams that have nothing to do. And this works magically. I'm super happy with the result. How this works will be a whole talk of its own. This will come, but it's looking really promising. It can process data in batches. It needs to it streams data, so the amount of data needed in memory is way lower. We will also make it out of order eventually, so if it doesn't fit into memory, the in-memory state, we will spill to disk, and we will do this in an efficient manner, in an informed manner, so no caching. But you as a database or as a query engine, you know what to spill and what to load way better than the OS does, because you have information of what you're doing. It's way more cache efficient, because if you work on one chunk at a time in a thread, and it's NUMA aware, so this chunk will stay on this thread. So when the filter is done, then the select can operate on the same chunk, and the data is still in cache. So different from the batch engine, if you churn through a whole column, at one point you will be memory bound, because the prefetcher cannot load data from memory fast enough into cache. And here the data will stay in cache. And we really see this in arithmetic. For instance, we see a 10x speed up. What's a downside is that order maintaining has way more overhead. So window functions will probably be a little bit slower. But that's sort of, there's no best solution for everything. That's sort of there are trade-offs. What we want to do is, we have an optimizer, and the optimizer can decide on which engine this should run if it fits. So there's work to do there. This is another, here you see a query on the new streaming engine, and in the batch engine it's really easy to run this query, because you can access all the data all at once. So let's say you have a pandas query, and you want to access the latest value in a DataFrame. It's easy because you have that whole thing in memory. But if you stream data and you stream it from this, accessing the latest value is really hard. You need to store it in memory. You cannot do this in a streaming fashion, right? Or a sort is also not streaming. You need to have all the data before you can apply the sort. So we need to rewrite POLIS queries. POLIS is a very versatile expression engine, or very versatile expression language. But we actually have to rewrite those expressions to a lower level IR that fits our new streaming engine. So that's what you see here. You see a filter, and then a sum. And some operations are streaming, but some are not, and we have to lower it. So you get these rather complex looking query plans, but they work really great. Yeah, and as I said, because of the cache efficiency we see, depending on the query, we can see a 10x performance increase. And also because you tend to load way less data in memory, your cache invalidation is just way less. And finally, for the large data, we're building POLIS Cloud. We started building this 3-4 months ago. We still have a lot to do. this will be two things. It will be an async runtime. So imagine you're writing polars on your laptop and you want to run a query and want to do something else. In the meantime, you can publish this query, let it run serverless, and you get a join handle, which you can await later. So it's similar to async computing. And you could do this for thousands of queries. And it will be very handy, for instance, in data orchestration, like Airflow and Prefect, where you have a very lightweight orchestration node that determines what should run, but you don't want that thing to be beefy, right? You don't want to do queries actually there, because so you can dispatch that to a cluster. And we're building distributed polars. We want to do this a bit differently than Spark, because we are really good in vertical scaling. Vertical scaling has gotten way more interesting, right? We have way more RAM, and the amount, the work that can be done on a single CPU is way more than 10 years ago. It's also way less overhead, because you send data between threads, which is just pointers, and sending data over the network is really expensive. But having multiple nodes has also benefits that you can extract more data from S3, for instance. You have higher data speeds if you can just parallelize horizontally, because on a single node you're limited to a certain bandwidth. But we want to, so in Spark you would go pretty horizontal. We want to go 4 or 5 nodes maybe, and then vertical scaling. So you get the maximum download bandwidth, but still the benefits of vertical scaling. Yeah, so we're working on this. We expect private alphas, betas somewhere next year, but this is all very much work in progress, but something we're working on. The new streaming engine will be released in a few months. We're already supporting a lot of operations. We've got group-wise working, we've got joins. We're starting on joins. We've got all the batch operations working, and we can dispatch back into the default engine. So we're almost there. Yeah. So as a recap, we want to have a DataFrame API for any scale. We focus on empowering you on your laptop. That's where it starts. And if you need more, we want you to be able to scale out with polars. Thank you.
Do we have any questions?
If you're author of an expression plugin, how does it interface with the engines, like the streaming engine and the GPU engine?
The GPU engine, it doesn't, because so for those who don't know, Polars has a plugin system which allows you to create your own plugins, and they will compile to an expression that will be the Polars engine will hook into that expression. You will have native support, so you will get parallelism for free. You get Rust. You get the same performance as if it would be written by Polars. The in-memory engine has full expressions plugin support. The streaming engine, it depends on the flags of the expression. So the expression, the expression can have a flag that it's element-wise. And if it's element-wise, we can just apply that. If it's not element-wise, for instance, a sort needs all data, then we cannot. What we will do is we will update the plugin system to have a instantiate, update, finalize, and then you can keep an inner state. But we still have to figure out that is something we want to do. We have to do this internally for some expressions as well. So yeah, good observation. For the GPU, it's not really possible, but yeah.
Great presentation. So the first question I asked is related to the GPU. I remember the benchmark you showed there I think one of the bar shows like, I think it's number 6, it shows 0.8.
Yeah.
That means GPU optimization with basically GPU is run slower compared to controllers.
Sorry?
So that means by adding the GPU, like the query actually runs slower compared to.
Yeah, I think what happens here is we're I/O bound, and maybe there's a little bit of difference in the Parquet reader. So here we dispatch to the GPU Parquet reader, which if you're I/O bound, and I think Parquet CPU GPU is. I think Parquet decoding is so complex. I'm not entirely sure that the GPU will be fast, but I need to leave that to the NVIDIA guys if they know that. But 0.8 or 1, I would call that as no difference. It's not something I think if you 1.3, number 2 is 1.3. I would call those the same speed. Yeah.
I have a follow-up question on this. So, in this PDS-H benchmark, what kind of like DataFrame operation usually see the biggest performance gain? For example, in like when we think about DataFrame, we can divide into some categories, like whether it's the join, whether it's a window function, whether it's like pivots. Like,
Yeah.
So which are the things that benefits most from using GPU?
Joins, definitely joins and group bys. Those do a lot of compute, a lot of hashing, a lot of partitioning, and GPUs are great for that. So Query 21 and 18, I believe, have 5 or 6 joins next to each other. The PDSH benchmark is, the TPCH benchmark is very DataFrame or database oriented. So it's a lot, it doesn't fit DataFrame usage perfectly, I would say, because there's a lot of, I don't think it's very common that you write 8 joins and you have your data normalized, right? It's so it's it isn't the best benchmark for data frames. But then again, there's also not really a data frame benchmark that covers these broad queries. Yeah.
Any more questions? Okay.
Yeah, there.
So one thing that when I think about making a streaming pipeline, data pipeline, that a challenge that can come up is what if you have a stage that you need to, let's say, call a machine learning model in your pipeline, and so like you need to chunk your data a little bit into a different size, and then call the model and come back into the Polars pipeline. Have you guys thought about that kind of support?
Yeah. Let me see. We have. I don't know if we use it here. We have. So as you can see, we can multiplex. We have a multiplexer, and we can here have an in-memory sync here, for instance, and there we can just accumulate this data and continue here and wait there. If we go out of memory, then the runtime can decide to spill this side and keep this one in memory and call back into your machine learning model. If we need to run a Python function that has the flag that it needs all the data, we will store it into a memory sync, call that function, and then we call this ready to send. So we have a DAG, and we have all this message passing, and the whole graph can determine when it's ready, what needs to be blocked. As I said, we can have a whole talk on it, but it will be able to do this. It will be way more powerful than our memory engine. It can also support different outputs, for instance. So that's something we cannot do at the moment. If you write collect, you will get one output, one data frame or one sync. So we have a multiplexer in the engine, and we can actually stream to different syncs. Yeah. Cool.
Last question? Okay, thank you.